forward to, okay. All right, so, all right, now let's go, in case anybody wants to view these in a secondary effect. All right, so, and maybe to help people find it a little quicker if they're kind of running through the videos, is to write up here, chapter 24, number 39. Okay, so let me just read it out loud to myself here. It says a long straight wire surrounded by a hollow metal cylinder whose axis coincides with that of the wire. All right, so I'm going to maybe draw a wire here first. So here's going to be my wire. Okay, and then it says a long straight, a long straight wire is surrounded by a hollow metal cylinder. All right, so maybe I'll just draw this. Maybe I should give a little bit of thickness to it. There we go. Hope that came out well. I'm trying to make something look 3 dimensions. It's not always so simple to do. Okay, so there's my picture, both in my head and on my piece of paper here. All right, the wire has a charge per unit length of lambda. Okay, so there's this lambda, and just for illustration purposes, I will put a plus all the way down the wire in the center. Okay, and keep reading here. The cylinder, okay, this is good, has a net charge of, so maybe I'll point to the cylinder here, of 2 lambda. From this information, use Gauss's law to find the charge per unit length on the inner surface and the outer surface, and the electric field inside the cylinder, a radius r from the axis. I'm sorry, outside. Okay, so when we do a Gauss's law, and let me maybe do a cross section of this. So here would be the wire itself in the center wire is what we like to call it. And then this, which we often call the shielding wire, I'll draw out here. Okay. When I go to find the electric field, and I know the question on B just says find the electric field outside of the cylinder. So I'll do that one first. But I think to answer the other parts in A, we've got to do the other regions. So maybe changing colors here, I'm going to draw, and in case anybody missed it here in the lecture and the material, this mathematical surface called a Gaussian surface isn't a real physical surface. It's something we can do an integration on, and it's to help us understand what's going on here. So Gauss's law says this, and that's what we're asked to do. So let's find the electric field. And so it is E dot dA, and that's equal to the charge that's inside the Gaussian surface over epsilon naught. Okay. So now remember, and I'll put it in this drawing, the center wire has a charge of lambda. That's what we did over here. And this outer wire also has a charge, I'll just make a little mark, of 2 lambda. That charge is going to become important on the right-hand side, but I'll do the left-hand side first, because the first part of this is to take the dot product and then use symmetry arguments. And I know I ran through this a bunch of times in a lecture, so I'll do it kind of quickly unless you really want me to spend much time here. But here's how the argument goes. The argument goes, if the charge is symmetric, it must be the same value everywhere on this Gaussian surface. So, knowing that this is a constant magnitude, I can remove it and pull it in front of the integration. That's a part of our calculus. The other part of the argument of symmetry is because it's symmetric, the electric field must be pointing radially outward. And that is the same direction as the area vector. So there's no angle between the electric field and the area vector. So that's a 0. And that then is a 1. And let me switch back to my Zoom so I could see you shake your head. Yes. Okay, good. Yeah, you were there. All right, beautiful. Okay, so then I'll have this field, and what that has done is what started to look like a really hard kind of a math, multivariable math, that's what, math 200 problem, has now been reduced to not even really calculus, but more of what I call reading the math. This is just saying right here, hey, this says add up all the area. Well, when you add up a bunch of little areas, you get the whole area. So this right here is just the whole area. Now, coming back to this picture here, you know, making a Gaussian surface all the way around it, like I showed in this cross section, I would also have to make that Gaussian surface of some length. Let me call it length L. So if you wrap around it, and this morning I was doing a cylinder out of these sticky notes, so I'll do that again. So if I make a little cylinder here, and kind of picture this as, you know, sitting right here with the wire down the center, you're really asking what is the surface area of the sticky note. And if you unroll it, you can see it better. This along here would be the circumference, and this right here would be the length. So that's why the area would be the circumference 2 pi r, and that would be the length. So that's how I would do the math on the left-hand side of the equation. Now, on the right-hand side of the equation, this right here means what is the charge inside of this Gaussian surface. So, what is meant by the charge density is this is the charge per length. So if we were to take what I'll call the total charge density, because see this inner wire has a charge density of lambda, and this one has 2 lambda. So the total charge density would be adding the 2 together, because both of them are inside of my Gaussian surface, and then times how long we would go in our Gaussian surface. So I'll come back to this picture. This picture is a length L. Excellent. And then as I look at the math, I see that the L's cancel off. And in fact, I would probably pause and say that's probably a good thing, because what this is saying is that the electric field has nothing to do with how long I make the Gaussian surface. Remember, the Gaussian surface is just this mathematical tool used to find the real physical thing called the electric field. So if it had depended upon the length that I draw the Gaussian surface, that would be concerning to me. This should ultimately not depend on how long I draw the Gaussian surface. All right, and I can see it doesn't, so I'm happy that. And now I can add these two together, so that's a 3 lambda. And then if I put the 2 pi and the epsilon together, and then the r, I think I've answered the question. What is the electric field outside? And in fact, before I go back to part A, let me scan down the solutions and see, did I get what they got? Yeah. Oh, now they did say radially outward. So I implied that while I was doing the solution, but I should come back here and write it at the solution level. So there is the equation of the electric field. Okay, you good with that?
Yeah. Thank you.
Yeah.
Yeah.
Okay. Now hang on. I'm not done unless you want me to be done, because you also asked about A, or I haven't done A yet.
Yeah.
All I really did was find it on the outside, and the reason I did that is I thought seeing that logic would help, because the part A says the charge per unit length on the inner and the outer surfaces. Okay, so this one I'm hoping is now the easier step. Maybe I should have put B here, and now I'll put A, and I'll come back to this picture, because if I put a bunch of pluses in here, and if I had done this, I wasn't asked to do it, but if I was asked to find the electric field in here, all of these steps would have been exactly the same, except right here, because the charge enclosed, when I make this circle here, I'm not including these charges that are on that outer conductor. It's only the inner one.
Yeah.
So because of that, I would have only had a single lambda.
Mm-hmm.
I'm not sure where to write this equation. Maybe I'll write it down here, because again, you're not asked in this problem to actually solve that. But that's what it would have came out to be. But here's why I'm pointing that out. Because also, if I was asked, and I wasn't, but if I was asked to find the electric field inside of the metal of this outer conductor, this shell out here, what's the word they used? Surrounded by a hollow metal cylinder. So in the metal cylinder itself, because it's a metal, I would know the electric field is 0. And so that was one of the lessons earlier on, that the electric field must be 0. So now I can finally answer their question. So if there is a field here, but yet when it gets in the metal, it's 0, that means negative charges must be pulled inward and are on this inner surface with just the right concentration to stop the field from these. So since these were created by a a charge of lambda, these on the inner surface must have a charge density of negative lambda. So then the inside surface must equal negative lambda. They must be exactly the right amount and of the right type to stop the electric field. So the electric field was generated down here as positive, and as it's heading out, they've got to terminate because it's got to come to zero inside the conductor. And the only way they can be terminated is with negatives. So there's the negatives.
Okay.
And we've got to terminate all of them, but not generate more. So they've got to be exactly the same value. Now, with that in mind, then the outside surface would have to be 3 lambda. How do I know that? Well, coming back to here, remember the total on the outside surface needs to be 2 lambda. I'm sorry, not on the outside surface, sorry. The total needs to be 2 lambda on the whole thing. And I already have a negative lambda on the inside. So all of this charge on the outside needs to be enough so that when I include both the outside and the inside, I get 2 lambda. So that's why the outside needs to be 3 lambda. So when I take the outside of 3 lambda and add it together with the inside surface of negative lambda, the total is 2. And I see you shaking your head. That's a good sign. And let me just check the solutions. Oh, good. And they said the same thing. So okay. I didn't mess up.
Yeah. Thank you.
Ah, you bet. All right. Let me come back to my Zoom on here. And I think I said Chase was next here. Yeah, Chase. Okay. Can we do number 50? What is that? 57. Okay. Sure, you bet. Okay, so let's come over here and go, what is this, chapter 24, number 57. All right, let me switch back over to the question here, the 57. What is 57? Oh, a non-uniform charge density. Yes, yes. And of course, it's copied in black and white, but I have a suspicion this is a magenta one. I'm kind of tempted to look over at the book and see, but better not. Not worth the time. Okay, so number 57, it says a spherical symmetric charge distribution has a charge density of, and they give a little formula, and I'm just going to write that first. So the charge per volume, which is some number A, which they haven't said what A is quite yet, over R. Oh, I'm just going to keep reading. It says where A is a constant. So we just know it's some number. They don't give us any numbers. I think that kind of makes it a little harder problem. I think problems where they actually give you a number and they say, you know, A is 17 and you plug it in makes it easier for students, but leaving it as a variable is important and a good skill to develop. So they're, in 121, we often put a number there, and now we leave it as just a constant. So we don't know what that number is, other than we know it's a constant, and that's going to be important. Okay, find the electric field as a function of R, and then they give us some helpful hints here. So let me draw a picture. They say it's a spherical symmetric, so I'm going to draw maybe a cross-section of a circle. Maybe I'll even try to make an equator, dot, 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 dot. See if maybe that looks three-dimensional somewhat. I don't know, does that help at all? But the real key is to realize that this must be an insulator. We know it can't be a conductor because they said there is a charge density to it. It's got charges spread out throughout the ball. Okay. And then they say find the electric field everywhere. He didn't say it until he got into the suggestions, but in the suggestions, he says call the radius of the sphere capital R. So I'm going to put that in my diagram here. And so coming out to here is, make it a little bigger so you can see it, capital R. And I would say there is 2 steps to this. One step is what happens if you're talking about inside, and the other one is what is you're talking about outside. Or does he only ask for just one of them? Evaluate the integral. No. Find the electric field as a function of R. Yeah, now he doesn't say whether that's inside or outside. So I think he wants us to do both. So let me begin by saying, all right, let's do the inside. Inside. Okay, so now the inside, we'd be talking about values of R that are less than capital R. So I guess I would write it down here in terms of mathematics. All right, so let me start with Gauss's law. So here's the integral over a closed surface. Here is the vector E. Here is the dot dA. Here then is the charge inside of the Gaussian surface. And here's the permittivity of free space. So starting there with Gauss's law. And now would be a good time, now that I read it, come back over and see your guys' faces here. See if anybody looks confused, and particularly who asked this again? Chase, okay. Chase, do I see you? Or... Oh, there you are. Okay, okay. Yeah. All right. And okay, so taking this and kind of the magical technique of this chapter is learning what Gaussian surface to make, because if we make the right Gaussian surface, this is an easy integral. We make the wrong Gaussian surface, this is a whole super hard integral. And usually the key is a Gaussian surface that has the same shape, so we can do a bunch of symmetry arguments. So my Gaussian surface over here is going to be a sphere also. And it's going to be then a sphere which is inside of this charged ball, because that's where I'm trying to find it. Because that first big step, taking the dot product, can really reduce things right here. And here's how the argument goes. I think you heard me do it a couple times in the lecture, and I'll keep saying it here. That if the charge is symmetric, that is, if you're standing on this surface and you move to this surface and you move to this surface, and you kind of imagine yourself actually inside the ball. Kind of like, I don't know if any of you watched the old Magic School Bus videos when you were kids. And but if you imagine that you went on this Magic School Bus and you actually got inside of this charged ball, and if you were standing right here looking around, what charge distribution would you see? Because if you were to stand on some other part of this Gaussian surface and look around, I claim you would see the same charge distribution. And it's because of that we could say that the electric field, even though we don't know its value, would be the same on that Gaussian surface, because we know from the physics part of this that the electric field is created from those charges. So if the charges look the same, it must make the same field. So that's half of the symmetry argument. The other symmetry argument is something if you were to draw a line through it, you know, and kind of, this is my hand, flip it over, what charge distribution would you get when you flipped it? And I would say because it's a sphere, if I start here and flip it, I would get the same charge distribution. So whatever field it must be making, it must make exactly the same thing. So whatever direction it's pointing, it must mean when you take that direction it's pointing and flipping it, it should still be in the same direction. And the only thing that could work for that is along that line of symmetry. Because if you were pointed something off the line of symmetry and you flipped it, you know, so if it was like pointing where this pin is pointing, which I need to hold the pin, right? So if there's my hand and my fingers are kind of the direction of the symmetry, but the field was the direction of the pin, if I flip it, it doesn't point in the same direction. The only way I can flip it and get it going in the same direction is if my fingers and the field are in the same direction, and then I flip it. They're still in the same direction. All right, so that's our argument that the electric field, even though we don't know too much about it, would be in the direction in a line of symmetry, which is radially outward, which is also the same direction as the area vector. And so therefore, the area vector and the electric field must be in the same direction. So again, we use a bunch of conceptual physics arguments here to make this integral actually very, very simple. What started off looking like a hard integral has now just boiled down to something that I would even call we have to do the integral. We just interpret the integral. We read the math. This is saying add up the little bits of area, and that just means you'll get the total area. And since this is a Gaussian surface, the total area is 4 pi r squared. Yay! Okay, so there is the part that maybe I took too long, because I don't think you were really asking about that. That was not the main part of this chapter. That's something you saw in the lecture and you saw in the book. This was just for anybody who probably still struggled or didn't quite catch it. What you are asking about, I think, is the harder one right here, is how do I get the charge inside of my Gaussian surface? And let me point out then, coming maybe back to the picture, and at the risk of making my picture too complicated, maybe coloring in my Gaussian surface, it's the charge inside of this Gaussian surface. And that is not all of the charge on the sphere. There's a lot of the charged sphere that is beyond this Gaussian surface I've made. So what am I going to do? Well, that's where this comes into play up here, the density. Because the definition of charge density was the amount of charge in a small volume. So what I'm going to do down here in this equation is the following. I'm going to leave the epsilon naught alone and say that this, the charge inside the Gaussian surface, is a summation of little chunks of charge that are inside of this Gaussian surface. I'm going to write it like a calculus term. And so in my mind, here's what I'm picturing. I'm going to add up that square and that square and that square and that square and all these squares, they're really cubes, that are inside of this Gaussian surface. I'm not going to add up these out here. And of course, there's no charges out here, but Even though there's charges here, I'm not going to add them up because Gauss's law says it's just the charge that is inside. So that's what this means. But let me keep going. Integral. All right, so let's, I got to bring it close by here, do a change of variables. Let's replace this dq with rho dv. So coming back to this part of my equation, this would be rho dv. And they said that the rho was this A over R, good. Now, dV is part of the hint. It's also part of what you did in your calculus, but let me kind of try and draw a picture. I'll kind of do a two-dimensional picture. And since my picture got kind of messy, I'm going to draw a new Gaussian surface here. So imagine this is my Gaussian surface. If I wanted to know the total charge inside of this Gaussian surface, I might add up a shell, another shell, another shell, another shell. And so in your calculus class, you probably call this the shell method. Add up a bunch of shells. All right, so what I mean by that is then right here in this equation, this is the charge density in that shell, which remember from the equation means each shell has a slightly different charge density. And then this would be the volume of a shell. So let me just color one of the shells and ask, what would be the volume of a shell? Now this one's kind of hard to show. I've been using earlier on these sticky pads to make cylinders. Spheres aren't so pretty, and I don't know if I can make a sphere. Maybe this way and this way. But if you could imagine me. I have a baseball or something nearby. But, oh, I do have a ball here. All right. So let's take my little baseball from my Macy's Father's Day catch at Dodger Stadium here. All right. And so if I were to put this piece of paper and, wrap it around this sphere or a piece of aluminum foil, and then if I were to unfoil it, the foil would have been the shell. And when I unwrapped it, if I were to ask how much volume does that shell have, I would say it is the area of the paper I wrapped around the sphere and then times the thickness. All right, so coming over here and looking at my equation, this right here then is the volume of this piece of paper wrapped around that sphere, a shell. So its area would be the surface area, 4 pi r squared. And the thickness is where the calculus would come in. I would call that a dr. And that's really the big step in the problem. You're shaking your head. I don't know if that's where it was the hang up for you, but that's
farther on when they
okay.
So it wasn't dependent on the R's. That's where I was kind of getting hung up.
Oh, okay. So a little further. Okay, so you're good there, but I'm sure this was helpful to many others. Okay, so then continuing on now with the mathematics, starting with first canceling one on the bottom with one on the top. And then also, like any calculus problem, I'll look for things that are constants and pull them in front of the integral. And so now we just have r dr. And then if I then do, as we said, the shell method, coming back to this little picture, we're going to start with our first shell that has radius of 0. So my limits here would be first shell has radius of 0. And I'm going to keep going to my last shell, which I would say is what we called the Gaussian surface, R. And so this integral becomes r squared over 2 evaluated from 0 to r, which when I plug that in, that just becomes r squared over 2. So I'll just scribble that out. Now, if I understand your question right, to get the electric field, E, I got some algebra to do. But notice that there is a 4 and a pi on each side, so that'll cancel out. But then here's the part of your question. Notice that there's an r squared on both sides of the equation.
So at first, I thought they were different r's, but now that it's not the whole r of the sphere, it's just the r of the surface. That I think that's where it was.
Yeah, and let me expand on that because that is a common mistake for a lot of people. And what you're pointing out is back here on this integral. Where do I go? Do I integrate from 0 to little r or 0 to big R?
Little r.
And in this case, it's little r. And here's the reason why, is you are coming back earlier in this equation, trying to find the charge inside the Gaussian surface. So you would stop at the Gaussian surface. You would not go all the way out to the capital R. Now, I'm glad you say that, because watch the second half of this problem. The second half of this problem is what I will call outside. That is, little r is greater than capital R. And so if I redraw this, oh, I should do it in red since I did it in red before. If I redraw the charged sphere of radius capital R, but now I draw a Gaussian surface that is bigger than capital R, although I'll still label it with a lowercase r for its radius, then everything over here is still the same with one exception. And the exception would be what you're pointing out. That is, when I go to add up my shells, look at this picture. Oh, no, go back to the equation. Remember, this is saying add up all the shells because right here, you want to say, what is the charge inside of the Gaussian surface? But when you're outside the ball, you would only add up to capital R, because once you got further than capital R, there is no more charge there. Now, it's true you're still trying to find the total charge inside the Gaussian surface. But the reason you would stop at capital R is because now you've just run out of charge, not because you got to the end of the surface.
Yeah.
And so that's the main difference between inside and outside. So maybe to finish this problem, if I come back and say, take this line, E equals 4 pi r squared equals, and 1 over epsilon naught a 4 pi, and then as I said, on this case, we'll go from 0 to capital R. This would be capital R squared over 2. I guess technically I still have a 4 pi that cancels off. But as you ran into, these r's would not be the same. So I'm going to leave the little a and the capital R squared here in the numerator and move the 2 and the epsilon and then the R squared. So this is what I would get on the outside.
So they must have left a portion off on the solutions then.
Yeah, well, and it's part of the question. Let me come back to what was this again? 57?
Yeah.
Yeah, so 57 only does the inside, huh? And stopped. Let me go back to the question. Why a spherical charge, find the electric, see, yeah, poor word. It says just find it as a function of R. It should have said where R is less than capital R.
Yeah, because I was like, there's no way that the R's cancel out if it was outside.
And you're absolutely right. So that's a good sign. Sorry they confused you, but I think you learned something there.
Yeah.
Yeah.
Okay.
Excellent.
Yeah. Thank you.
Good, and hopefully others did too. That's always a common mistake. Where, where do I stop the integral? The real question is, just remember, you're trying to get the total charge inside the Gaussian surface. And so you do it a little different when you're inside versus outside, whether it be a sphere or a cylinder or whatever your shape is. All right, well, good. Let me switch back over here to my Zoom. Let's see, that was 57. I would like to sneak in with a 121. Okay, perfect. Who was this? Right. Where are you? Okay.
So I've got a three-dimensional vectors problem for you. I was hoping you might be able to help me with.
Okay, yeah, sure. Fire away.
So I've got plane 1 is a horizontal distance of 2.06 kilometers directly east of the tower. It says, the first thing says, use a control tower as the origin of a 3D coordinate system.
Okay, so I'm going to try and draw a 3D coordinate system. There's always a debate on what you want to call the X and Y axis, but I'll go ahead and say that the X axis, I'm trying to draw coming out of my paper.
That's sort of the standard way I know of.
Okay, and then the Y axis is kind of to the right. And then the z-axis is up. Okay, so
I got plane 1 is a horizontal distance of 2.06 kilometers directly east of the tower at an altitude of 0.962 kilometers.
Okay, I'll pause right there. All right, so this is the control tower, and a horizontal distance and an east. Now, traditionally on a compass rose, you call the x-axis east. So I'm going to do that, okay?
Okay.
All right, so on the x-axis, I'm going to come out to maybe this mark right here and say that was, and just correct me on my numbers, is it 2.06 kilometers?
2.06 kilometers east, yeah.
Okay, so that's along the x-axis. But then, of course, we go up because it's a plane. It's in the air. It's in the z-axis. So how far up? And then up?
0.962 kilometers up.
Okay, 0.926 kilometers up. Okay.
962.
Oh, 62. 62. Okay.
Right. And then.
So in my picture, so this would be plane number 1, right about there. Okay.
And then plane 2 is 4.01 kilometers directly north at an altitude of 3.28 kilometers, and they want the distance between the two planes.
Okay. Let me try to draw it in the picture. Let's see. So north. Now, again, traditionally on a compass rose, north is the y-axis, so I'll do that. So let me come along my y-axis and go out to about this mark. And so, and just correct my numbers here, this looks like a 3.28 kilometers.
Yep, that's right.
And,
The other one's 4.01.
oh, that's north is 4.01.
Yep.
Sorry. 4.01 is how far north, so that'll be along the y-axis.
Mm-hmm.
And then on an altitude of, and so this one's quite a bit higher than the other plane, 3.28.
Mm-hmm.
All right. So I'm going to take you back to your math class. I'll start with 2 dimensions. Let me save this piece of paper when I come back. But if I had a 2-dimensional grid, and this is the x-axis and this is the y-axis, and I had point number 1, which we'll call x1, y1, and point number 2, which is x2, y2. And if you were to ask how far away are those 2 points, you would do Pythagorean theorem.
Mm-hmm.
And so this part that I'm pointing at, or the along the horizontal, would be the difference of those 2 x values, and the vertical part would be the difference of those y values.
Mm-hmm.
If we call the hypotenuse here d, then Pythagorean theorem says that d squared would be the x between them and the y's between them squared, right?
Mm-hmm.
So you good with Pythagorean theorem?
Yeah.
Okay, so the same thing is also true in 3 dimensions.
Okay.
So coming back to here, I would say that the distance squared between these 2 planes is, how far apart are they east and west, the x-axis? How far apart are they north and south? That's the y-axis. And how far apart are they in altitude? That's the z-axis.
Okay.
All right, so putting in my numbers. Let's do the x's first. So the first plane, as you said, was 2.06 on the x-axis. And the other plane on the x-axis was 0.
Mm-hmm.
Now, on the y-axis, the first plane was 0, and the second plane was at 4.01. And on the z-axis, the first plane was at 0.962. And the other plane, where was it? Ah, there it is, 3.28. So grabbing a calculator, this first one would be 2.06, and I'll square it. This would be a negative 4.01 squared. I won't bother to type the negative since it is squared. And this would be 0.962 minus 3.28, close bracket, and squared. And so that'd be the square of the distance. So if I then took the square roots, I'm looking at 5.07 kilometers. Yay.
Okay. 7. Okay.
Look like you still have a question, or maybe you haven't formulated.
I'm just trying to process, like, in my brain what we just did, because I mean I see.
All right.
So
Let me come back a step. When I did it in 2 dimensions, did that make sense?
yeah.
Okay, where is it? Oh, it's under here. Yeah, so I would say I'm doing exactly the same thing.
Okay.
I'm just saying, look, I want to find the distance. And what is called the distance formula in a math class is really Pythagorean's theorem. Find how much over x, how much over ny, and use Pythagorean's theorem.
And so you just did that, and you just added z to the equation.
Yeah, and the same thing works in 3 dimensions. A little harder to visualize if I were to draw a line connecting these two. You could do something like this if you wanted. You could first do 2 dimensions and get the distance on the ground, how far apart they are.
Mm-hmm.
If you wanted to do that, do Pythagorean's theorem once, and then get that for Pythagorean's theorem a second time. Pythagorean's theorem in 3 dimensions is really doing Pythagorean's theorem twice in 2 dimensions.
Okay. I think I follow you now.
Okay.
Cool. Thank you.
Okay, well, keep asking. All right, let's see. Looks like we got Renee. I have 102 questions. Oh, good. Okay, 102. Hi, Renee.
Hi, they're very easy, I think. For number 24 on chapter 2, there's just a formula that I didn't catch in your lecture, and I was wondering if that's like, that comes from a different formula or is something that you went over and I missed. It's the d equals 1/2 at squared.
I had a feeling that was it. Okay. I don't think you missed anything in the lecture yet, to answer your question.
Okay.
I usually leave this for students to work on a little bit, and then I say something. So I think it's coming up next week in next week's lecture.
Okay.
But with that said, since you asked it, I'm going to go ahead and show you. This is what the author used. Let me show you. That is actually a combination of 2 equations you did see. Let me change my desktop back so I can see your face and see if you're see if your eyes are saying yes or no. Okay, so tell me if this equation looks familiar. That distance equals to average speed multiplied by time. Good with that one?
Yep.
Okay. Then the second one that I think you're good with, but let me not put words in your mouth, is that acceleration is the change in velocity over time. You seen that
Right.
one? All right.
Mhm.
And I claim that the one you're asking about right here is actually those 2 put together, and I'll prove it. All right, let me begin. But, and there's an important step in the proof that you, and if anybody else in 102 is watching, should see. Let's start with average speed. How do you get average speed? Well, you take the initial speed, add it to the final speed, and divide by 2. So if I gave you 2 numbers and I said, give me the average, I'd say, okay, take the first one, and then take the 2, add them together, divide by 2. Fair enough?
Mhm.
All right. And so let me work with this equation. The acceleration, the change in speed would be final minus initial. So I don't know if it's important, but notice here I'm doing a plus sign because I'm taking the average.
Mhm.
And here I'm doing a minus sign because it says take the difference. Okay. Now, here's why I wanted you to see this proof, and you will see this, like I said, in a lecture coming up, is that let's look at the special case if the initial speed is equal to 0. Because what I want you to get out of this little discussion here is this equation is the combination of these 2, but only if the initial speed is 0. And I want to emphasize that because should only use this equation if your initial speed is 0.
Okay.
See, and that's not the case in every problem. Some problems do start off with velocity equal to 0. And if that's the case, then feel free to use this. But this is why I didn't show it, is this is a special equation. So you should really understand these two first. You should never just jump right into this one.
Mm-hmm.
And because initial speed is nowhere listed in here, it's easy to start using this equation even when the speed is not equal to 0. So I want to prove to you that this equation does work out, but it only works out when this is true.
Okay.
Right. So watch this. So if I take that first equation and say distance equals, and if I set the initial speed equals to 0, I get final over 2 multiplied by time. And if I do this equation, I get final speed over time. Then if I move t to the other side of the equation, I get final speed equals a over t. Now, if I use that, and this is the part I was saying, that if I combine these two equations together, so here's distance equals, and then right here at final speed, I'm going to put AT, and I still have a 2, and I still have a t. And so the last step here is if I simplify this, I can write it as 1/2 AT squared. So you might see this equation already, and you are going to see it quite a bit in the lab. You're going to see it a number of times in class, but hopefully I will keep emphasizing that this can only be used if the initial speed is 0.
Okay, so free fall and
Well, now, okay, be careful with the word free fall. I would say free fall that you let it go.
okay.
Because if I were to throw it down, we still call that free fall once my hand lets go of it.
Mm-hmm.
But because I threw it down, the initial speed's not 0.
Okay, so it's just a combination of the acceleration formula and the average
Yeah,
uh,
exactly.
velocity formula.
Yeah. So some students choose never to mess with it. They just always go back and do this step first and then get a number and then put it in here.
Okay.
Other students say, well, I don't want to do 2 steps. That's more work. I would rather just do 1 step. And that's cool. No problem with that. But just remember, you wouldn't use it for a case that started with a non-velocity of 0. And in fact, since you took your time and came in here to ask a good question, I'm going to give you a hint. It's not just you. I give it to everybody who asks this question. On the test, I give 2 questions involving asking for distance. The first one has a initial velocity of 0, and the second one does not.
Okay.
And some students will use this equation for both
For
of them.
both.
And it's only valid for the one. And for the other problem, where the initial velocity is not equals to 0, you got to go back to the fundamentals and actually do these 2 steps.
Do them one at a time.
Yeah.
Okay. And the second one's not really like a question per se. It's number 10. The number 10 you have on the homework sheet, when I look at the answer in the back, the question that you gave is number 9. So I didn't know which one you wanted us to do.
Oh, let me see here. So let me open the homework for your class 102. So far, everybody in 102 has just kind of read me the problem and done a good job. Okay, so it says number 10, right?
It says number 10, but when I look at the answer that matches the question you're asking is number 9. So I don't know if you want us to do 10 or do 9.
I do want you to do 10.
Because like the answer is 2.4
Oh,
miles per hour.
wow.
And that's the answer for, I think 9 was the one that matched in your solutions.
Yeah. Interesting. Yeah, that's just a typo on the the solution guide here that you're looking at. It's from the author. And that's weird that they didn't match the solutions.
I don't know if in the book that the question you're asking if it's 9 or.
Well, I'll tell you what. Let's not try to figure out whether it's 9 or 10, but let's actually. It's a good problem, as stated. So let's call it number 9, I guess.
Okay.
Even though it says number 10, but it's a good problem. It says starting at 9 o'clock, you hike for 3 hours. Yeah, I don't know what happened there.
Okay, no worries. I just won't
But
do
obviously
10
you knew
then.
what was going on because you were able to tell that the correct solution was number 9. Yeah.
Well, I checked the answer and was confused, so. But I think
Yeah, and
that's
I
it.
apologize for the confusion, but I would say that you figured it out, so you're better off for it. You looked at it and go, that's not right, and then you looked at the one above it and go, that's the one.
Right.
Yeah.
All right, well, thank you.
All right, and come back with another question. Hang around if you want, or
Sure.
whatnot. Okay. All right, let's see. I'll go back here to the Zoom here. What do we have after Renee? Daniel, after those 2 questions, I got one from chapter 24, number 11. Okay.
Yeah, so I was just wondering if you could explain part B to me, and then I also have a quick question about 18 after this.
Okay. Hey, can you shoot that in the chat? So it looks like somebody's waiting here from 121, and they're probably real short and simple, and so I want to make sure I get to them. All right, so back to 24, number 11, and then let me switch here back to the homework for the 122 class. Okay, so chapter 24, number 11. Now, it sounds like you weren't asking about the whole thing. It sounds like there was
Just part B, yeah.
just part B through the flat face. Here, well, I need to come back and read it here. So a particle of charge Q is located immediately above, as shown. Okay. Let me draw a picture. Yeah, this is actually a great one that I was helping with the students in the first Zoom session. That remember this, okay? To look closely at the physical picture. Some of these can be made a lot easier if you look at the physical picture than actually doing a calculation. And this is one of those examples. The other one that I did this morning was number 4. But if I were to put this charge Q right above, then the electric field going outward would look something like this in my picture.
The same in all directions, right?
Yeah. And you know what? I know you didn't ask about A, but just in case somebody's curious or they're watching the video, let me backtrack to A for a second. Oh, in fact, yeah, this is like we were talking about number 4. Good, because you said you were going to work on visualizing these. See, in A, this is what I would do. I don't know if this is how you did it, but this is how I would do it. I would say in A, if I did a surface that was a sphere, okay? Now bear with me. Remember that this is not a sphere. This is a hemisphere, okay? But if I did a sphere, so if I did one like this, then this side of the equation would be calculating the flux. I guess I would call it the total flux.
Okay,
And
so it'd be flux times charge inside?
Okay, so wait, before I get too far, I'm just trying to say that the left-hand side would be all of the flux going through this sphere. Okay?
Mm-hmm.
And that would equal to the charge enclosed by that sphere, which is all of it, Q, times epsilon. Fair enough?
Yeah.
Now, here's how you were supposed to make A real easy, is then you look at this picture. And you look at this picture and you say, okay, of all this flux that is going through the sphere, the bottom half goes through the hemisphere. So the flux through the hemisphere must be 1/2 of the total flux, which then must be 1/2 Q over epsilon. And
That's so much faster.
yeah. So again, if it took you more than 3 seconds, you're missing the visual picture. Mm-hmm.
Okay.
All right. So I don't know how you did it, but I'm glad I went back to A because that's what they were kind of hoping for. You would either the easy way. Otherwise, you'll spend way too much time on this homework, and you'll run out of time on a test, anyways. You may not run out of time on homework. It kind of depends what else is going on in your life. Okay, so then, and here's the part B you were asking about. And again, it's visual. So I'll bring it back in front here. Notice that in this picture, the flux that goes in the flat part of the hemisphere is the same that comes out of the rounded part. So if we just said in A that this is the flux coming out of the rounded part, then the flux going in must be the same number. Of course, we call n negative, so if we want to say it's a negative value, fine. And so there's the answer to B. What's the flux going in?
Okay, so since the flux going in is the same, wait, so the flux going in is the same amount going out, right?
Mm-hmm, mm-hmm.
So it's basically the flux of the flat part.
Uh-huh.
Okay, is wait, so sorry, could you just explain why it's why it's negative again?
Yeah, and I'm just going to
Just trying to understand it.
I'm going to come back to the solutions. Do they call it negative? Yeah, they do. Good. All right. So here's the mathematics of this. Okay.
Mm-hmm.
This number comes out to be positive when these are in the same direction.
And
So
that's the curved part, right?
So right. So any electric field going out of a surface would be positive. And that's this curved part. It's pointing out of this. Let me highlight the hemisphere a little better. Right. This stuff's all coming out down here in the rounded part. So that's why I would say the flux is a plus.
Okay.
And then this stuff going in, and that's the key going in. You can see it. It starts where the charge is and it goes in, goes in, goes in, goes in, goes in. And so
Yeah.
So same magnitude,
Okay.
but with a negative sign.
Okay, so since it's going in, it's okay.
Yeah.
Okay, cool.
Cool. All right, let me come back over here to, I think there was a good question about 121, and I know that you guys in 121 and 102 might be, once you get too bored, the 122 people got some real hard stuff, so we're doing a lot of good stuff. I also have a quick question from 121. Who was this? Mark. Mark. Where are you, Mark? Did I lose you? Oh, there's Mark. You're muted, Mark.
Yeah, my question was just about area per time unit conversion. It says that Whenever you're ready.
Yeah, go ahead. I'm listening.
It says that, okay, cool. It says that a forest is being destroyed at a rate of 10,400 square kilometers per year.
So
And
10,400 square kilometers per second. A little choppy. Is that what I heard?
per year. Yeah, per year.
Oh, per year. Okay. And what's being destroyed? I'm kind of curious on this problem. Surface area?
A forest.
Oh, a forest. Okay.
Like an
So this would be
Amazon
like
forest.
okay, I see. So we're destroying the Amazon at 10,400 square kilometers per year. Okay.
Yeah. And then the question asks, how long would it take for the size of a soccer field, like 7,960 meters squared? How long would it take to destroy like that? I don't know why I can't word it, but how long would it just take to destroy the forest the size of a soccer field, which is 7,960 meters squared?
Read that again. 7,900?
Yeah, 7,960 meters squared.
60 square meters is the size of a soccer field. Okay.
Yeah.
All right, let me, I guess I'm going to take you back to maybe your algebra class, but it's also your physics class. You just haven't got there. But what does something mean by this word rates? I'll forget the forest for a moment. If I said I was riding my bike at a particular rate, what I mean, I would say, and I'm riding my bike at a rate of 20 miles per hour.
Yeah. So distance per time.
Okay, right. But a rate just means per time. It doesn't necessarily mean distance.
Okay.
So the destruction of the Amazon forest is a rate.
Mm-hmm.
And you wouldn't use distance because you're talking about a surface area.
Yeah.
Surface being destroyed per time. Okay.
Yep.
Now, I'm just going to call this capital R for rate. Because if you take rate and multiply it by time, that is your total. So if this was my bike, I would call my rate my velocity. Velocity multiplied by time would give me my distance. So if I was doing a rate problem for my bike, the rate would be a velocity, okay? And you're gonna do that real soon. But let me cross that one out. You're doing something more general. You're saying the rate of destruction of the Amazon forest multiplied by time would then give you the total that was destroyed in that time. So if we put in a time of 1 year, for example, we would put in a rate of 10,400 square kilometers per year. And if we put in a time of 1 year, years would cancel, and in 1 year's span, we would have destroyed 10,400 square kilometers.
Yeah.
Fair enough?
Yep.
All right, so now let's get to your problem. So here's your problem, okay? Your problem looks like this, and I'll just write, so here's total, here's rates, here's time. You're given the rate of 10,400 square kilometers per year. You do not know the time it takes to then reach a total destruction of a soccer field, which would be 7,960 960 square meters.
Exactly, yeah.
All right, so that's the first big step. But there's I think a second, even harder step coming up here. Because now I want to solve this for time. But in order to do that, I need to make sure my units of area are the same. And I'm sure that's why this is a homework problem, because you're learning how to convert units. All right, so there's different ways of converting units, but let me show you my favorite. Let me jump down here and remind you of a little bit of mathematics. If you had x times y and you squared it, what that means is you take the x squared and you take the y squared. Now, why do I bring that up? Well, let's come back here to the problem. What this is really saying here is you have a kilo squared and a meter squared. Now, the reason that is useful is because now I have square meters that can cancel with square meters. Of course, now you're probably still wondering, well, wait a minute. What about that kilo? Well, a kilo means 1,000, so I'm just going to change that to 1,000 and square it.
Yeah, I saw your lecture on treating them just like numbers, and that's why I'm coming back with this, because you explain it like.
Oh, good.
Yeah, I just wanted to kind of see it again, but yeah, this is helpful. Thanks.
Okay. And out of my own curiosity, it sounds like you've already got the algebra, but I'm kind of wondering how quick, then, if these are real numbers. So I'm going to do the math here. Maybe I will start with the 10,400 and multiply it by 1,000 squared. So that's this number over here on the right-hand side. So I'm going to then take the 7,960 and divide it by all of this. And this comes out to be 7.65 times 10 to the negative 7. And I better watch my units. When I bring this over, it goes into the numerator. So that's years is equal to t. And although that's helpful, I still don't have a good grasp of it. So I'm going to replace years with 365 days. That's what a year is equal to. And that's what you were saying. How do you convert units? Just do a direct substitution. I would do this too. Well, what's a day? Well, a day, so let me just replace day with 24 hours. So this would tell me how many hours it took, and that might be more useful to me. So times 365 times 24, wow. And so this is 0.0067 hours. Even that I'm not convinced is very useful. So I'm going to do one more conversion. An hour is 60 minutes. So I'll just replace an hour with what it's equal to. So take that number and multiply by 60. That is 0.402 minutes. Wow, and even that I think might be better written. And that's under a minute. That's under half a minute. But maybe to put it in seconds, I'll just replace minute for what it's worth, which is 60 seconds. And so now I will finish with the number of seconds. And so that's 24.1 seconds. So if this was a real number, I don't know if it is or not, then the Amazon is being depleted, and a soccer field is being depleted every 24 seconds.
Thanks a lot.
That's crazy. Okay, you bet. You bet. All right, let's see. Where are we here? That was 121. Me too, Jonah. Okay.
Hello.
Hello. Was that a question, Jonah, or?
Oh yeah. No, I have a question on air traffic controller vectors. If you've gotten one of those already.
Oh, you know what? Yeah. Somebody was just asking about that, and I drew a picture, and I'm not sure where you're having troubles with.
Setting up the problem.
Okay, let me come back to the picture I drew. Maybe I should just draw it again because it's kind of neat to see it. Let me do this because you got to really visualize this.
Mm-hmm.
So this is the x-axis coming out. This is the y-axis. So this would be, traditionally we call the x-axis east. And traditionally we call the y-axis north. So I'll stick to that. And we usually call up, that is the altitude, the z-axis. So in that problem, they say plane number 1 is 2.06 Is that really? Here, I'll mute him if I know how. There we go. Okay. All right. First time I had to do that. My wife teaches too. She got a Zoom bomb or some guy came in, started just dropping F-bombs. Like, F you, F you, F you, F you. It wouldn't stop. She's like, how do I mute this? So I haven't had any of that. So anyway, that's my first chance to mute somebody. Okay. All right. So back to your question, Jonah. All right. So Jonah, so this one said the first plane is 2.06 kilometers to the east. And it then said it had an altitude of 0.962. Okay. The other plane was to the north. So let me draw that along the y-axis. That was 4.01 kilometers. And then had an altitude a lot higher at 3.28 kilometers. All right. Now, before I go any further with this, I want to jog your memory back to your math class. And maybe I'll even just get a new piece of paper for that. If I just had a two-dimensional grid, this is X, this is Y, and I had a point here, let's call it X1, Y1. And I had another point over here, let's call it X2, Y2. And I had a question that asked how far apart they are, call it distance D.
We have an equation for that.
Yeah, this is Pythagorean's theorem. You would say, okay, how far is it horizontal? We would call that the delta X.
I was thinking distance formula, but that's easier.
Okay, and then, so this is the distance formula. Distance formula squared would be the x squared plus the y squared.
Oh, right. That's, yeah, that is where that comes from.
Okay, so yeah, the distance formula is Pythagorean theorem. Those are kind of one and the same.
Uh-huh.
Okay. Hey, I like your image. Is that a quartz crystal or is that?
I don't remember. It's a crystal in a New York museum. I can't remember what it was. Though. It might be quartz.
Yeah, it looks kind of like a smoky quartz, a smoky I forget what element is in the smoky quartz. Makes it that dark color.
Yeah, it's the size of a person in real life.
Whoa.
Yeah, it's huge.
Oh, okay. I can see why it's in the museum then.
Yeah.
Yeah, I got a little one about the size of the end of my thumb in my rock collection, but
Oh, that's cool.
yeah. Okay, all right. So sorry, I got distracted. All right, so back here, then the same thing is also true in 3 dimensions. Distance between 2 points squared. So if I just kind of drew a connecting line, it would be equal to how far apart are they on the x-axis squared? How far apart are they on the y-axis squared? And how far apart are on the z-axis?
Okay.
So in this case, it would be the first plane on the x-axis 2.06 and minus 0, because the second plane, has a coordinate of 0 on the grid. The second plane, for the y-axis, the first plane has a y coordinate of 0, and the y-axis is a -4, or sorry, it's a +4, but I'm subtracting it. And then the z-axis might be the harder one of it. The z-axis would be the first one, 0.962 minus 3.28 squared.
Oh, okay, I see.
And I'll do the math if you want, but I had done it earlier for another student, and it looks like we came up with.
Yeah, I have different numbers, so I'll have to do it different. But I see how to set it up now. Okay.
All right.
That's it though. That's the whole thing.
Yeah, so that would be the distance. Unless there's another question. One thing I need to figure out from you, 121 people, is how to see your homework questions. I haven't been able to.
Have you not been able to see one?
Yeah, are they on the Canvas page?
No, we have this. I think Doug made it himself. It's a script Doug Google. I don't know. It's like his own system.
Okay.
You could have the 121 students share their screen with you.
Yeah, you can do that, but you have sharing screen disabled.
Okay. Oh, I do.
Yeah.
Well, okay. I can change that, but do you need to show me? I think I understood the problem.
No, yeah, I mean, yeah, you had the same. You described.
But what
the
I
same
was getting
problem.
at is it would be nice on Thursday night to kind of look over the problems you guys have. So I'm gonna figure. I'll email your instructor and say, hey, where are you posting those so I can look at them.
Yeah, it's his own website. I'm pretty sure he made it himself.
Okay.
It seems like it.
Okay.
But yeah, thank you for the help on this one.
All right, good. You are welcome. All right, let's see. Got a bunch of papers here. Move those over. Okay, who was after? Oh, how are we doing on time?
I think you missed me. I asked a question earlier and then you went down.
Oh, I'm sorry. Go ahead, Anthony.
So this first one's pretty quick, and I think you have to take a break as well. Your time's been up, but
well, if it's a quick one, let's do it first before the break.
Yeah, this is just a conceptual question for 122.
Okay.
If you have a charged particle and then you surround that charged particle in a sphere that is got the same charge, a hollow sphere with the same charge, what would happen to the charged particle in the middle if you made the radius of that circle smaller? If you just kept making it smaller and smaller, so the forces would be pushing on each other.
Oh, okay. Say that all again so I can draw a picture here. Say it again.
If you have a charged particle in the middle of a sphere of a
I have a charged particle, and it's in the middle of a sphere.
That's the same charge.
Okay.
If you take that sphere and you make its radius smaller, so the radius of that charge of the sphere that's charged the same is compressing inward towards that charged particle, what would happen to the particle in the middle as the compressive forces keep pushing on it?
Okay, so let me just start here. I think I understand the picture here. What we have is a charge that's inside a charge sphere, right? And so what you're asking is what happens now if this sphere on the outside is lowered, right?
Yeah.
Okay. Now, here's something that's kind of a little shocking, but important. Let me draw a new picture. Just the sphere with the charges. Let me not worry about the one inside there, because the force on the one in the inside is really the charge you put there times the electric field. So I'm just going to ask, what is the electric field inside from all of this? And I run through it, but the answer is 0.
Yeah. Now I see what you're saying now. Yeah.
So if you make it smaller, the field is still 0, and the force is always 0.
It would be 0. Yeah.
So it's always 0. Yeah.
So that particle would that particle just stay still and do nothing?
Yeah. There's no force on it. Yeah.
Okay.
Back to Newton's first law. If it's at rest, it will remain at rest. If it was already moving, it would keep moving.
Okay. I was thinking like, as the particle continues to get compressed, what would happen? But that answer makes much more sense. Despite being
good. Hey, I want to see. So I know it's past time for break, and I could use a little bathroom break myself. But and you guys can take a break anytime. But I see John here from a lab question, and that would be nice to address that, because I don't think that'll be a long one. And if it's 102, we probably should deal with it. John still in here? I don't see John. Is there more on the next page? I don't see another page. All right. We missed you, John. Maybe hopefully he sent me an email and I can do that. Ooh, 121. Wait. Okay, wait. Let's do this one too. Sorry, I'm not sure exactly how to pronounce your name. Bilikov, but let me see if I could answer this one. This is from the 121 class. Do you want to unmute the light cove, I guess? But it says here a large pizza radius is bigger than a small pizza's radius by P. Not sure exactly what that means. Maybe it's just a symbol. P, is that plus or minus a percentage? The large pizza area and price is bigger than the small ones by 77%. Find P of R.
So this question is it's a scaling problem, and I posted the whole solution on the discussion. If the person's not here, so
yeah,
they could check it on the discussion.
Okay, or maybe we'll come back after the break. Why don't we take a little break? I think he checked out for a little bit, so if it'll be okay with you. It looks like I don't see any more questions on the chat, but I do see some new people like Hunter here who might have one, and Timmy's back here. So, but anyways, break time, and I will see you in 33 minutes. All right, bye now.